today's topic is atomic orbitals, and you will be able to explain and predict how electrons are placed into their orbitals. So let's take a step back into an earlier lesson for our think and answer. Right, this diagram over here shows 5 different electron energy levels, and the question is, how many different frequencies of visible light are emitted by hydrogen based on the transitions between these elements, these energy levels. So let's see. So here you see drawn in all the transitions to the ground state, right? You can go from energy level 5, 4, 3, 2, 1. So there's 4 transitions from higher levels to the ground state. Next, there's 3 more transitions to energy level 2, producing visible light. And we see there's 2 more smaller transitions to energy level 3, producing infrared light. So that's a total of 10. So as a reminder, this question does come up often, where it'll ask you if a electron in hydrogen drops from energy level to energy level 1, what type of electromagnetic radiation is emitted? In that case, you would say ultraviolet, all right? Because this is all ultraviolet. This is all visible, dropping to 2. This is all infrared, dropping to 3. Okay, so electrons and the uncertainty principle. Right? So Heisenberg's uncertainty principle states that it's impossible to accurately figure out both the momentum, meaning the speed, and the position of a particle simultaneously. Basically, if you go to measure the velocity, you're going to affect the position of an electron. Now you know the velocity, but the positions change. You cannot know it anymore. If you go to measure the position of electron, you'll affect the velocity. And you cannot know both things at once. All you can do is calculate the probability of where the electron is likely to be. So an atomic orbital is the space, it's the 3D space around the nucleus in which there's a 90% probability of finding the electron. And the shapes of those orbitals depends on the energy of the electron. So an analogy for this, right? Let's see. So if you're in a classroom, right, say it's a school day, it's third period, your room is room 223. You are 90% likely to be in the confines of that room, right? There's a 10% chance you're not there. Maybe there's a small chance you're in the hallway, small chance you're in the bathroom, a chance that you're on the train, even a chance that you're home. But more likely than not, you're in the school, in that room. And the shape of that room dictates where you are, right? So your orbital, if you're an electron, your orbital is like a box. It's the shape of a box. Assuming like you're flying around all over the room. So an orbital just describes where an electron is most likely to be, and it kind of shows the space. What is the shape of that space where the electron is moving around? When an electron is at an orbital of higher energy, it can be further away from the nucleus. The probability of it being further away is higher in that case. Okay, so this lesson, there's going to be a lot of terminology that's going to sound similar and overwhelming, so just bear with me. So, main energy levels, right? Energy levels are also referred to shells, are labeled using N, right? That's already a lot. So, the first energy level is the ground level. It's the closest to the nucleus. That's energy level 1. That's lowest energy. Then you have energy level 2, a little further out, right? More energy, so the electron can be further away from the nucleus. And then energy level 3, it's even more energy, right? The electron has so much energy that it's not as attractive to the nucleus anymore, so it can be further out. Okay, so each energy level contains a certain number of sublevels and a certain number of orbitals. Sublevels are S, P, D, F. Those are the sublevels. right? So energy level 1 has just one sublevel. It has S. 2 has S and P. That's two sublevels. 3 has S, P, and D. So we see that energy level 3 has three sublevels. And 4 has S, P, D, F. So you get the gist. That's as far as you would need to know in terms of sublevels. And then, so you have whatever your energy level is, that's how many sublevels you have. And in each energy level, you have a certain number of orbitals. So energy level 1 has 1 squared orbital, so 1, right? 2 has 4 orbitals. 2 squared is 4. 3 has, you guessed it, 9 orbitals. And the fourth energy level would have 16, oh, not even there, 16 orbitals. So that's already a lot of terminology, right? You have your energy levels, you have your sublevels, and in those sublevels, you have orbitals. So here, we get to see a little visual of what orbitals look like. So the smallest orbital is the s orbital. S for sphere. Oh, hold on. All right, so basically, an electron in the s orbital is moving around in here. It's confined to the space. Every once in a while, it might step out, right? But mostly 90% of the time, it's in this space, in this circularly shaped space. And it can hold 2 electrons, right? So there's only one shape for s orbitals, just the sphere. So this is the s orbital on the first energy level. If you look at the s orbital on the second level, it's bigger, meaning the electrons don't have to just be in the center anymore. They can move further apart, further away from the nucleus because they have that much energy. 3s, they can move even further than that because they have more energy. So this is the lowest energy orbital in every level. Every level has an s orbital that is its lowest energy orbital. Okay, now you have the second sublevel, which contains p orbitals, right? You see px, this is a dumbbell shape. This px is oriented on the x-axis, py oriented on the y-axis, pz oriented on the z-axis. Each of these orbitals can hold 2 electrons, so 2 here, 2 here, 2 here. That's a total of 6. So if we look at the first energy level, this, oh, hold on. If we look at the first energy level, it only has this in it. The second energy level, we said had 4 orbitals in it, right? We got that by doing 2 times 2. 2 squared is 4. So it has the 2s, the 2p, 2p, 2p. There's 4 orbitals. The p orbitals have more energy than s. So here we can see again, in a nicer shape. This is easy enough to draw. If you're asked to draw it, you just draw like an eternity sign, an infinity sign. So if you're asked to draw P on the x-axis, you'll draw it here. Y-axis, Z-axis, you'll just draw it out, whichever axis. In reality, they're not separate like this. Actually, before I say that, let me clarify. This whole loop is one orbital. This is not 2 separate orbitals. This is just the shape of the one orbital looks like this. So in reality, all of these orbitals are in the same place, right? So there's 2 electrons that are hopping around out of existence in this p z orbital, and then there's 2 more hopping around through here, and then there's 2 more hopping around through here. So the p orbitals contain 2 electrons each, so a total of 6. Now if we visualize it, the second energy level we said had the p orbitals and the s, so altogether this is what they look like overlaid, right? So this can carry a total of 8 electrons in those 4 different orbitals. So now here's some more shapes. You are not responsible for knowing them, right? So the third orbital shape, slightly higher in energy than p, is this, the d orbitals. They have a variety of shapes. You do not need to know them. You just need to know that there are 5 of them, and they are higher in energy than p orbitals. Similarly, the fourth orbital shape is the f orbital. There are 7 of them. You do not need to know the shape. You know they can carry a total of 14 electrons because each orbital can carry 2. Okay, so let's break this down a little bit. Move my face out of the way. Okay, so vocabulary. Principal energy levels, right? We have energy level 1, 2, 3, 4. In this example, we're looking at energy level 2. Why? Because energy level 1 in n equals 1, there's just the one s. In n equals 2, that's the energy level, there's 2s, and there's the 2p orbitals. So there's 3 of them, right? We can see them right here. So this over here is the whole energy level, which inside it contains subshells or sublevels. So 2s is a sublevel which has 1 orbital in it. All the s sublevels have exactly 1 orbital in it, shaped like a sphere. The higher the energy level, the bigger the sphere, the bigger the space the electrons take up. Then we look at the p subshell. The p subshell has 3 orbitals in it. 1, 2, 3. Each can fit 2 electrons, right? So this energy level has a total of 4 sublevels. I'm sorry, a total of 4 orbitals. Okay, so you guys got the gist of this. So this brings us to the apartment analogy, apartment building analogy. So if we think of it as an apartment building, right? This is an apartment building without any stairs, and full of lazy people. They don't want to climb up unless there's no space on the first floor, right? You're not going to the second floor unless first floor is packed. You're not going to the third floor unless both the first and second floor are packed. So how does this work? So let's see, energy level. We'll say energy. Oh, that didn't work. Level will be like the floor, right? Sublevel will be an apartment. Orbital will be like the rooms in an apartment. How many bedrooms are there? And electrons, let's say they're people. And you can fit 2 to a bedroom. So, using this analogy, the first level, the easiest one to get to, takes no energy at all, has 1 sublevel in it, right? 1s. It just has the 1 sublevel. So let's draw that as a square. The second level has 2s, right? Not as in there's 2 of s, but it's the sublevel is 2s because it's in the second level. That also has 1 room, 1 orbital. But the second level also has an apartment with 3 rooms in it. The third level has this like tiny apartment as well, the S apartment, but it also has the P level one, 3 rooms, and it also has one with 5 apartments in it. I mean 5 rooms in it, right? 3D. So you get the gist. The level tells you how many apartments there are, how many sublevels there are, right? First floor has 1, second floor has 2, third floor has 3, fourth floor has 4. The s orbitals, this type of the s sublevels always have exactly 1 orbital in them. The p sublevels always have 3 orbitals. The d sublevels have 5. The f sublevels have 7. Okay, so here, just like a quick diagram for you to figure out how many sublevels there are, how many orbitals, and how many electrons can they hold. So the energy level, that straight up tells you how many sublevels, right? You don't have to do anything. The number of orbitals, you square what your energy level is. And how many electrons? Well, however many orbitals you have, you can fit double that many electrons. So take a second, pause, try this, and then hit play. Okay, so as you can see, it's pretty straightforward, except for one little part, which fortunately you don't need to know. So the orbitals, you need to know your s orbital, you need to know your p orbitals, but your d orbitals, you don't need to know these names. It's too complicated. You just need to know that there's 5 of them. And same for the 7 orbitals. You just need to know that there's 7 of them. Skip this. Right, this is basically telling you the same thing. Okay, so this is your orbitals laid out in with energy as the y-axis, meaning as you climb up, the further up you get, the more energy that sublevel, that orbital has. So we can see right away that energy level 1 is the lowest energy, and it only has one sublevel in it. Energy level 2 is higher, and we can see of the 2 different sublevels, 2p has more energy than 2s, and 2p's got 3 orbitals in it. Now if we look at energy level 3, we see overall it's higher in energy than energy level 2, and it follows the same pattern where 3s is the lowest, then 3p, then 3d. Right, we can also graph it out this way, and here the circles show you how many orbitals there are in each level. So it's pretty much what you would expect, except for one weird hiccup, right? This order, so this order is 1s, then 2s. Oh, my pen's not working. 1s, then 2s. 2s, then 2p, right? It's SPDF, that's the order. 1s, 2, so finish 1, then 2 is S and P, then 3 is S and P, and then D, but then we see that there's this weird overlap between the 3D and the 4S. So everything follows the appropriate order of like 1s leading to 2s to 3s to 4s, and the sublevels being in order of S, P, D, F, except when you get to this part. There's a weird overlap. I'll show you a convenient way to remember that later. Okay, so when you do electron configurations or orbital diagrams, there are some rules that you have to remember. The first one is called the Aufbau principle, building up. You start from the bottom, then you go up, not the other way. So what do? Let me just show you a couple of examples. So hydrogen has 1 electron. That first electron goes to the lowest energy level possible. It goes to 1s. And every orbital can fit 2 electrons, right? So helium with its 2 electrons, the second one also goes into the same thing. And over here, you'll be doing this later, but you can see the electron configuration, which just basically tells you what orbitals are being filled with how many electrons, right? So this is 1s1, there's 1 electron in 1s. 1s2, there's 2 electrons in 1s. Lithium has 3 electrons. That third electron can't go into the first energy level anymore. It's full. So it's got to go to 2s, right? And that's represented in this electron configuration. 1s, 2, 2s, 1, because there's 1 electron there. So you get the gist. So however many electrons there are, you just have to put them in there, starting from the lowest energy level and then filling up as you go to the top. Hund's rule, also known as the empty bus seat rule, states that electrons will fill empty orbitals of the same energy before being paired up in an orbital. Think of it this way. If there's 3 rows of seats in a bus and 3 strangers get on, they're not going to double up if there's a free row of seat available. Why do electrons behave this way? Well, So when you have 3 orbitals in this p subbubble, all 3 of these have the same amount of energy. It takes the same amount of energy for the electron to enter any of these. However, there is a difference based on the fact that electrons are negative, right? If you have 2 negatively charged electrons, they will repel each other. They're not attracted to each other. They push each other apart, so they want to be as far apart as possible. And that is why, instead of doubling up within an orbital with another electron, an electron will move to a free or unoccupied orbital first. So out of these two options, the one on the right is correct because there is no empty orbital before doubling happens. So similarly here, Pauli exclusion principle is another rule which states that 2 electrons in an atom cannot be in exactly the same state. What does that mean? That means you could have 2 electrons in the same atom. You could have 2 electrons in the same energy level, in the same sublevel, in the same orbital. But once you have 2 electrons in the same orbital, they cannot have the same spin. That would be physically, literally impossible. They would have the same exact state in that case. So they must have opposite spins, and opposite spins are shown by showing arrows facing opposite directions. So in this case, the one on the left is correct. The one on the right shows 2 electrons in the same orbital with the same spin, which is not possible. Okay, so an orbital diagram, what it does is it shows the spin of each electron and it shows where these electrons are. The first thing you need to do in drawing an orbital diagram is locate your element in the periodic table. Right, so let's go to the periodic table. Okay, oxygen. We see that oxygen has an atomic number of 8, right? There's oxygen right there. The atomic number is provided, it's the number on top of your element. So oxygen has an atomic number of 8, which means it has 8 protons and it has 8 electrons. So oxygen has 8 electrons. So the second thing you need to remember is every orbital can fit 2 electrons. And you fill the lowest energy orbitals first. So that's 1s. So I'll put 2 electrons in here. Okay, now that 1s is filled up, I have 6 more electrons to go, which means I can move on to 2s. So I'll put 2 more here. All right, I have 4 more electrons to go. So we see that once we finish 1s, then we fill 2s. Once we fill 2s, then we can move on to 2p. So I have 4 more electrons to go. I'll put my first one here, second one here, right? Because we don't want to double up. Third one here. And now the last one, do I put that in 2p or in 3s? I have to put it in 2p because 2p is not full yet. Unless 2p is full, nothing can go to 3s. So this would be the final answer. Okay, so same thing for phosphorus, right? So let's find phosphorus right over here. All right, so phosphorus has atomic number 15. So 15 electrons. All right, one will go here, another will go here, and 4 here. All right, so once 1s is finished, we can go to 2s. After 2s, we can go to 2p. So I'll draw 6 more here. 1, 2, 3, 4, 5, 6. That's a total of 10. I need 5 more. So 2p is done. I'll move on to 3s, that means. So 1, 2, I need 3 more. 3s is filled, so I can move on to 3p. And I'll make sure they're in different orbitals. Right, so that's how you do an orbital diagram based on an element's atomic number and how many electrons. All right, so in this worksheet, we see orbital diagrams, 3 different orbital diagrams. Each of them is breaking a rule. So what we're going to do here is identify what rules are being broken. So the first one, let's take a look. The first one, we see there's a empty orbital in 2p, right? There's an empty orbital here, but there's a doubling up occurring. There shouldn't be any doubling up of electrons if there's an empty orbital. So what we're going to do is we're going to erase this guy. I'm going to move him and put him right here. Right, so that would be the correct version of that. So that was nitrogen. So now let's look at neon. What's wrong here? It looks like 2p has the right number of electrons, and they're all in the right places. However, if we look closely, there are 2 electrons with the same spin in this third orbital. So I'm going to erase one of those, and we're going to draw one in with an opposite spin. All right, so now that's correct. All right, let's take a look at fluorine. Fluorine, there's an electron in 3s. However, 2p is not full. So if 2p is not full, this electron cannot go to 3s. That electron needs to be also in 2p. So we'll draw it right here. All right, so the 3 rules are electrons will fill lower energy levels before going up to a higher one. They will not double up if there's an empty orbital in the same sublevel, and 2 electrons in the same orbital will not have the same spin. All right, let's try making our own orbital diagrams. All right, so here the boxes are already written out for you, and the orbitals are already labeled. In the future, you'll have to do that yourself. So here, all you have to do for hydrogen is first take a look at the periodic table and see how many electrons does hydrogen have. How do we know that? We see hydrogen has an atomic number of 1, so that's how many electrons it has. So we're going to put in exactly 1 electron for hydrogen, right? That's hydrogen. So that's done. Let's look at nitrogen. Nitrogen has an atomic number of 7. So we're going to put in 7 electrons. We're going to put 2 right away into 1s. Right, 2 more into 2s. And then we only need to put 4 more down, right? And 3 more down to get to 7. So we'll put 1 in this 2p orbital, another one in the second orbital, and another one in the third. They are not doubling up. Okay, let's look at sodium. Sodium has, let's find it, Na. It has 11 protons, 11 electrons. So do 11. So 1, 2, 3, 4, single, 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 double, double, double. Right, that's 10, and we need 1 more. So that's it for sodium. Right, so you see the pattern here with 2p orbitals and also with the d sublevels. You will put them in as singles first before doubling up. All right, let's try fluorine. There's 9. All right, so 1, do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Not the prettiest, but you get what I'm doing. Let me fix that. Okay, phosphorus. Let's do phosphorus. Phosphorus has 15. Let's do this. 1, 2, 3, 4, 5. My computer is being a little bit laggy, that's why this is happening. So that's 7, 8. You get the gist. 13, 14, 15. Okay, so now let's do the same thing, but not for atoms, for ions. So if you guys recall, an ion is an atom that's lost or gained electrons. So an electron is negative, right? If an atom loses an electron, if it loses something negative, it becomes positive. If it loses one electron, it has a +1 charge. If it loses 3 electrons, it'll have a +3 charge. An atom can also become negative if it gains electrons. If it gains 3 electrons, it'll have a -3 charge. If it gains 4 electrons, it'll have -4 charge. So it's pretty straightforward. So hydrogen normally has 1 electron, right? So if it loses 1 electron, it's going to end up with none. So we just leave that blank, right? Had 1, ended up with 0. So let's do the same thing for nitrogen. Nitrogen had 7, ended up with 3 extra, so 10, right? So 7 to 10. So we're just going to draw 10 in here. But I'm not going to waste your time by going through all of this in the video. I think you can get how to do this. So I'll just show an example again with sodium. Sodium has 11 electrons, but this sodium ion has a +1 charge. That means it lost 1 electron, and now it has 10 electrons, right? And you would just fill in the orbital diagram the same way you did previously. All right, so that is it for today's lesson. Oh, one more thing. So we see here, orbital diagrams can be laid out with everything next to each other, flat, going to the right, increasing in energy, right? So 1s and then 2s is higher, 2p is higher in energy, 3s, 3p, so on and so forth. Or if you have energy as your y-axis, it could be laid out this way. So now we see that energy increases as you go up, not as you go to the right. Either way is fine, but if you see energy as a y-axis, you want to do it this way, right? This way. All right, that's it for today's lesson.